This is video number 29 in a series on foundations of arithmetic, algebra, and graphing. I'm Bill Kinney. It's part of a sub-series on decimals, real numbers, and percentages with an emphasis on calculator usage. It's part 8 of that sub-series. In the last video, part 7, we finally got to seeing why this real numbers part of the title is in this sub-series, because we saw that there are some numbers, some decimal representations of numbers at least, that, well, you can make them up that don't have a repeating pattern, and because every rational number can be converted to a decimal with a repeating pattern, as we saw via long division, and conversely, every decimal with a repeating pattern, through a process similar to what I did here, can be converted to a rational number, a fraction where the numerator and denominator are integers. It seems that those two concepts are equivalent, and indeed they are. Rational numbers and decimal representations with repeating patterns are completely equivalent to each other. Real quick comment about that. That does not mean that the rational number representation, or the decimal representation of a rational number is unique. And in fact, you can look it up. It's very interesting that 0.9 repeating equals 1. It's true. Doesn't look true, does it? But you can look that up, and there are plenty of reasons out there. I'm not going to take the time to explain it in this video. There are plenty of reasons out there that show that 0.9 repeating equals 1. What does that really mean? What's the meaning of that? It means that numbers can have more than one decimal representation sometimes. And so it's just something to be aware of. Decimal representations are not, in general, unique. But I want to focus in this video on some other things. First of all, I want to just emphasize that the rational numbers seem to be all you might need for measurement. Got my ruler here. Draw a number line, and maybe I'll go ahead and use the ruler. Help me draw it. Say you wanted to measure the length of something from maybe this point to this point right here. Use the ruler to help. Measure it as close as you can. Each of these, 1, 2, 3, 4, 5, etc., those are centimeters. So it appears that the length of that line segment is about 8.2 centimeters. Let's just pretend this is 8.2, which would be 8 1/5, which, if you think about it, is 41/5. The quick way to convert that mixed number to an improper fraction is to take 8 times 5 to get 40, then add the 1 to get 41, and then use the same denominator of 5 there as you see out there. And if I had a length that was slightly smaller, pretend that number is 8.1999. I didn't draw it really that close to 8.2 as I should have, but I didn't have enough space. If that was the true length, well, theoretically, if our ruler was accurate enough or fine enough, we could measure a length of 8.1999 and distinguish it from 8.2. Oh, and by the way, maybe I should say that 8.2 has an alternative representation as 8.1999 with the 9s repeating. But 8.1999 with 3 9s that are not repeating is different from 8.2. Well, there are infinitely numbers in between these two numbers, even though they're really close together. For example, their average, 8.19995, halfway between this number and this number, is in there. Then I could take the average of this number with either one of these, say with 8.2, and I'd get 8.199975. That's between these two numbers up here. 8.199974, 8.199975346. There are infinitely many rational numbers between any two given rational numbers, no matter how close they are together. That's pretty amazing. It seems that the rational numbers are all you would need for measurement. But in the abstract, at least, that's not true. Maybe from a practical standpoint it's true because we can only measure things so precisely. But in an abstract setting, it's actually not true. And the ancient Greeks figured this out. And this is a cultural thing that everybody should know. If you make a right triangle where the length of one side is, say, 1 inch in this case, and you make it a right triangle, so you make a perpendicular over here, and you can use a straight edge and compass to help you make a perpendicular, but let's just draw it here. This is supposed to be a right angle. If this is a 1 inch, and this is 1 inch, what's the length of the hypotenuse? Well, we could draw it and try to measure it. Appears to be about almost 1.5. I didn't draw it perfectly. It should actually be closer to 1.4. Each of these marks is 1/16 of an inch. So it's not drawn perfectly, but it turns out from the Pythagorean theorem, which you may want to look up, you should remember, it turns out that the length of this side is square root of 2 inches. At least theoretically, if these are exactly 1 inch each, and this is exactly a 90-degree angle. That's square root of 2 inches. That's our symbol for square root of 2. What is square root of 2? It's a number that when you multiply it, it's a positive number such that when you multiply it by itself, when you square it, you get 2. If you try to estimate it on a calculator, got to have a square root button. Oh, got to get rid of that glare there. There we go. Here on this calculator, I have to press my second button, second function, and here's my square root. Square root 2. 1.41213562, blah, blah, blah. Evidently, there are decimals that are not being shown. That is true that square root of 2 is not exactly equal to this. If I type it in that way and square it by raising it to the second power, the calculator doesn't spit it back exactly 2. And in fact, no matter how many decimal places you would end up taking, you would not get exactly square root of 2. You just get approximations. Turns out it's fairly easy to prove that square root of 2 is not a rational number, and therefore its decimal expansion does not have a repeating pattern. And I think it's probably even true that it doesn't have any pattern at all. It's somewhat random, though each decimal place is, in theory, computable with enough computer time. So, in the abstract at least, turns out rational numbers are not sufficient for measuring every length or every area or every volume or any continuous quantity like an amount of time. In practice, the rational numbers are usually sufficient because you can only measure to a certain degree of accuracy. But it's something that everybody should know that the square root of 2, for example, is not rational. And the story goes that the Pythagoreans are the ones who discovered this. Pythagoras came up with the Pythagorean theorem, and he had followers called the Pythagoreans. And the story goes that somebody died once they found out that they were sacrificed. Once they found out that there were numbers that were not rational because it just went against their worldview. But now we accept it, and it's pretty much a cultural thing that everybody should know and you should be aware of. So again, the real numbers include both rationals and irrationals, and is something you should be aware of, though mostly rational numbers are all you need for measurement in most calculations.